Hi guys, welcome to the channel. So today we are going to start with the topic of complex numbers. So in the previous video, that is the part 1 of complex number, we have discussed a bit about the introduction part of complex numbers. So now we are going to address one very important question before starting out with the complex numbers. That is why we need to study complex numbers. That is what is the requirement of studying complex numbers. What is their significance? So let's try to understand the importance why these were introduced. So suppose we have small a and small b as the two natural numbers, and we have one condition, that is a is going to be greater than b. Value of a will be greater than b always. Now we have an equation x plus a equals b. So this particular equation will not be solvable equation. That is, you use any natural numbers. No natural number can satisfy this equation. You can put up any natural number and you will see that this equation will not be solvable for x. So natural numbers are extended to form integers, that is from 0 to plus 1 plus 2 plus 3 so on, and from 0 towards the negative side, that is minus 1 minus 2 minus 3 and so on. If instead of natural numbers we are having integers, then this equation is going to be solvable. So you can use the integers to make this equation solvable. For natural numbers it is not going to be solvable. So from natural numbers these were extended to form the integers. Now let's take another example. Now next equation will be x into a equals b, where a comma b are the integers and a is not equal to 0. Now this equation will also not be solvable for integers. So you put any integer here. No particular integer will be able to solve this equation. So integers are extended to form rational numbers, that is in the form of p by q. So this way rational numbers were introduced to solve such type of equation, that is x into a equals b, where a and b are integers. If this is not solvable, we were introduced with the rational numbers, that is in the form of p by q. Now here if a and b are rational number, then the equation becomes solvable. So this way rational numbers were introduced. So here if we take q as the extension for integers, so q is extended to r, you can say, having both rational as well as irrational numbers. Now take another scenario where x square plus 1 equals 0, or you can say some other equation, x square plus 4 equals 0. These are not solvable in R, that is for rational numbers. There is no real number whose square is a negative real number, right? So if we take equation x square plus 1 equals to 0, here you put down any real number. The square of any real number cannot be negative. Therefore the equation x square plus 1 equals to 0 is not at all solvable. To solve such equations like x square plus 1 equals to 0, x square plus 4 equals to 0, where we need the square of a particular number to be negative, Euler introduced us to iota. Iota is a symbol represented just like I. It looks like I and we pronounce is at iota. And the value of this iota is root under -1. So if we have some value known as iota, and if we are going to use such values of iota, then this equation also becomes solvable. So to solve such type of equations, iota was introduced, and from here complex numbers were being started. Now before starting to understand about complex numbers, we first need to understand what is this iota. So Euler used to call it iota as an imaginary unit also. So iota is an imaginary unit according to Euler, and using iota we are going to solve such problems. So starting out with the introduction of iota. Now, we have already discussed iota is equals to root under -1. So now we will discuss about the integral powers of iota. integral powers. By integral powers I mean positive integral powers and negative integral powers. So first we will discuss about the positive integral powers and then we will discuss about the negative integral powers. So first we will discuss about the positive integral powers of iota. So first and foremost we know iota equals to root under -1. Now if we square both sides we will get iota square equals to -1. For iota cube you can write it as iota square into iota. So iota square equals to -1 into iota, that will be equal to iota. Now for iota to the power 4 you can write it as iota square into iota square. So this will be -1 multiplied by -1, which is equals to 1. So therefore we are getting the results like iota equals to root under -1, iota square equals to -1, iota cube equals minus iota, and iota to the power 4 equals to 1. Now if you solve for the subsequent powers, what you are going to get is value of iota is same as iota to the power 5, and iota square is similar to that of the value of iota to the power 6. Similar is the case for iota to the power 7 and then iota to the power 8. This one you can move ahead also. So this will be iota to the power 9, iota to the power 10, iota to the power 11, iota to the power 12, and so on and so forth. You can go ahead. So this is about the positive integral powers of iota. Now we will discuss about the negative integral powers of iota. Now again we know iota equals to root under -1. So iota to the power -1, first of all we want to find out for iota to the power -1. So we can write it as 1 upon iota. For iota to the power -2 we can write it as 1 upon iota square. Value of iota square equals to -1. So this will be 1 upon -1, that is equals to -1. For iota to the power -3 we can write it as 1 upon iota cube. If you multiply the numerator and denominator by iota, what you will get is iota divided by iota to the power 4, and iota to the power 4 equals to 1. So we will get iota. Now iota to the power -4 can be written as 1 upon iota to the power 4, and iota to the power 4 equals to 1. So this will also be equal to 1, right? So this is about the negative integral powers of iota. So if we take one example, so if we take the example of iota to the power -999, we can write it as 1 upon iota to the power 999. Now if we divide 999 by 4, we will get 249 here, followed by a remainder 3 here, right? You can divide it and see. So we can write down like that: 1 upon iota to the power 4 to the power 249 into iota to the power this remainder, right? We can write it like that. Now iota to the power 4 equals to 1, and 1 to the power anything becomes 1, any power will be 1. So we are left with 1 upon iota cube. Now you can multiply and divide by iota. So we will be having iota divided by iota to the power 4. Iota to the power 4 is 1, so we are left with iota. which is the final answer. So this way we can use negative integral powers so as to solve these questions, right? Now one point to note here is that if we have 4 consecutive integral powers of iota, for example, iota to the power 51, iota to plus iota to the power 52, plus iota to the power 53, plus iota to the power 54. So this equation will always be equal to 0. Take any 4 consecutive powers of iota and their sum will be 0. Now we'll understand this with the help of this particular example. Now let's understand how the sum of 4 consecutive powers of iota equals to 0. So here we have iota to the power 51 plus iota to the power 52 plus iota to the power 53 plus iota to the power 54 equals to what? Right? Here out of these 4 terms we can take iota to the power 51 as common. So here we will be left with 1, here iota square, and here iota cube. Now iota to the power 51 is outside. 1 plus iota square is what? -1, plus iota cube is what? Minus iota, right? Now plus 1 cancels out with -1, plus iota cancels out with minus iota. We are left with 0. So iota to the power 51 into 0, which will be equal to 0. So that's why if we have any 4 consecutive powers of iota and we have the sum of all these 4 consecutive powers, we will be left with nothing but 0, right? So in the next video we will solve some more questions related to the information we have got till now. So far that's it for this video. Thank you so much for watching.